Hello, Reuben. Thank you very much for joining us. And welcome back to all of our attendees in person and on the webinar. Reuben, this is the people we're sitting with today. So we're going to get started again. As a note, this is the fourth of 5 sessions for the day. It is looking at half-cell potential and corrosion mapping. Reuben Barnes, our Managing Director, is kindly stepping in to speak and present the content. I'm William Ward, I'm the New South Wales Manager, Live and Silverwater. So we are recording these sessions, so please do be aware of that. And I'm happy to hand over to Reuben. Thank you.
Yeah, thank you so much, Will. Okay, I'm going to get started. So we're going to be talking about half-cell potential mapping and corrosion. Presentation's been put together over many years. However, Will and I are the main contributors to it, and this latest iteration's been put together by Will, so thank you so much. So for those of you who I haven't met, I see some familiar names and some less familiar names. My name's Reuben Barnes. I'm the Managing Director of PCTE. I'm a materials engineer by trade. I've been running PCTE for 21 years now. And so really happy for everybody to be here, and obviously this is a subject that's pretty interesting, and I think it's also potentially one of the subjects where I find that there can be a little bit less understanding, or it could be simplified a little bit too much out there in the market. So obviously we need to set the scene. We need to sort of look at exactly what corrosion is. So basically corrosion is a sort of a generalized term whereby materials deteriorate and degrade due to chemical and electrochemical reactions with their surrounding environments. In our natural environment and in our day-to-day lives, we mostly encounter corrosion in the form of rust. It's because so much of our built environment is constructed of iron or steel, and so that red rust is the main one that we sort of encounter. But obviously, most materials can corrode in some way, shape, or form. So obviously, corrosion of steel in concrete is our focus for this presentation, and effectively, the reason why this is of interest to us is because corroding steel inside of concrete will create deterioration, and it's probably one of the main causes for the deterioration of our structures. So getting it right is important, and also being able to test for it for monitoring and maintenance purposes and potentially repair purposes is also important. So these are the obligatory slides where we sort of talk about the corrosion mechanism. I go to a lot of presentations, and a lot of people sort of slide through these particular ones quite quickly, but I think that it's really important to understand exactly what we're talking about when we talk about the corrosion mechanism, because the tests that we're doing and the corrosion that we're actually seeing on our steel is all basically governed by these mechanisms. And the more that you can understand the foundational science behind what we're trying to do, the better that you can use the technique or investigate it. But starting off, obviously, reinforced concrete is effectively a composite material where you have your matrix of concrete with your reinforcing steel, carbon steel generally when we talk about this, but obviously there's other materials that reinforcing can be made out of, but let's just talk about carbon steel. The reason why this is such a great composite is because obviously we have the strengths and weaknesses of the materials in a mechanical sense, in terms of steel giving tensile strength and the concrete giving that strength in compression. There is also another reason why there's such a great composite, and that's because of the corrosion resistance that the concrete actually provides for the steel. And that's because concrete itself is quite basic. So we have on the screen there that big pH equals 13. So that that basic matrix that the steel is sitting in actually allows a sort of a reaction to occur. It's called passivation. And passivation, I don't think anybody really understands exactly what all of the mechanisms with passivation are, but effectively what happens is that there's a very thin layer on the steel that gets created by this basic environment, and that prevents corrosion from occurring on the steel. So hence why we have such a great composite. Now, obviously, out in the environment, the main sort of chemicals that a concrete structure will encounter, there'll be water, obviously, but there'll also be oxygen from the atmosphere, and we'll see why those two things are important in a minute. But effectively, they're part of the mechanism. But then we also have these reagents in our environments. Chlorides, if we have, if we're relatively close to the sea, so that's the sea salt. We could also have other chemicals attacking there, but then also in the atmosphere we have carbon dioxide, which can also obviously is there with the oxygen in the air that we breathe. So the effect of those two chemicals can be effectively they will there's a process of diffusion whereby chemicals where you have a high concentration on one side of a barrier will permeate into another material, and depending on the actual concentrations, what we'll see is this front travel through the material. That can happen with the chlorides or the carbonation. The effect of the chlorides is that it has the effect of removing this passive layer. With the carbonation front, what we find is that as it reaches the steel, it actually draws the pH and makes it more acidic, and then we get our passive layer tending to disappear at that point. Obviously, once corrosion occurs, we can then look at the chemistry behind exactly what's occurring. And for those of you that have studied redox chemistry, you'll understand that in redox chemistry, we generally have to have an anodic and a cathodic region, one providing the electrons for the other. And so the corrosion's occurring at our anodic region, which is where the iron is reacting with the oxygen that's being provided, and that's creating that ferrous oxide, which we know as rust. That has a much larger volume than the steel that it's replacing. And then at the cathodic region, that's the real driving force behind the reaction, and that's where our water and our oxygen are, drawing in the electrons and also providing the hydroxides. So what's important here is that we have both of these sort of half reactions occurring, and all of the environment and everything around that is really what's sort of drawing that. The resistance of the ions moving from the cathodic to the anodic regions, the ability of the oxygen and the water to actually reach the steel, whether we have that passive layer, all of those things are affecting the corrosion. Obviously, the detrimental effects of corrosion are that obviously if we have an increased volume, that's going to create internal stresses inside of our concrete. So what we tend to find is that we get an expansion, and then we have these stresses and cracking. Once that becomes quite severe, we can then have what we typically notice, which is either cracking, and then once that gets quite bad, we get drummy, and then once that gets very bad, we can have spalling. And then once the spalling's occurred, obviously the steel is exposed to the environment, and the whole thing becomes quite chaotic and quick, and we can move to total section loss of the reinforcing quite quickly. So that's basically setting the stage for the tests that we want to carry out. And I think that's a good point at this point. Obviously, We're here to talk about different testing devices and what sort of things are available. We have a few devices that we're going to be talking about the specifics of how they operate. The ProSec PM8500 is a half cell potential unit. It uses an iPad, Bluetooth enabled controller, and then the reference electrode. And we'll talk about each of those components from a technical point of view. There are also some configurations where we can put the reference electrode into a wheel and then into a four wheel, and that sort of assists with data collection. We're also going to talk about the force corromap. That's a corrosion rate meter. Also does half cell potentials. And then we'll also talk about the ResiPod, which is a resistivity meter. So these are the main sort of tools that we would generally use when we're looking at corrosion, on top of potentially, crack measuring and cover meters and things like that. So let's jump into our half cell potential measurements. Effectively, with half cell potentials, we're measuring the potential difference between the reference electrode and the steel reinforcing. It relates to the likelihood of corrosion of steel, particularly where we have chloride-induced corrosion. It's less appropriate in some cases where we have carbonation-induced corrosion or saturated concrete. Two things to highlight here is that it does not measure the corrosion rate. Okay, so a more negative reading does not mean anything in terms of the actual rate. It's more the probability or the propensity for corrosion to occur. And it doesn't give us any idea of what the section loss is. And you'll find this with a lot of the corrosion measurements. We're not directly measuring corrosion per se, we're taking some measurements that we can infer some things about the corrosion state of the steel. So if we go back to our corrosion mechanism, we can see that we've got our cathodic and anodic areas. And what we're effectively doing when we're doing half cell measurements is that we're making a connection to the reinforcing. We then have that connection running through a voltmeter, and then we're holding the reference electrode, which is this point just here, onto the surface. And we're measuring the potential difference between effectively this reference electrode and the steel, effectively directly over the spot that we're measuring. So we'll move that around. Let's talk a little bit about the reference electrodes. I think this is an important thing and it tends to get forgotten. I don't know how many people actually report what type of reference electrode that they've used during their measurements, and it's quite an important thing. So first things, obviously we have our Australian standard 2382.5 for portable reference electrodes. We require moist sponge contact. We need a calibration certificate, which is always important. And we need the ability to check it before and after using a standard reference electrode. The two main types of reference electrodes that we have, and just sort of talking about a reference electrode, generally what it is it's a metal or something like that inside of a solution, and it has the ability to create half of this reaction. So we have the copper sulfate, which is shown here, where we've got basically a liquid copper sulfate solution, and then the copper rod into it. We can also have a silver chloride reference electrode, same sort of setup in terms of we've got our electrolyte, which is our potassium chloride gel, and then we have our silver wire inside. The reason why I point this out, and there are other types, there's calomel, there's a bunch of different other types of reference electrodes, but all of those will give slightly different readings. And so it's quite an important thing to understand what reference electrode you're using, and also the effect that that would have on the readings that you take. For instance, your silver chloride will have a plus 100 millivolts reading as opposed to your copper sulfate. Okay, next point. Okay, so we're going to talk about some influences that occur when we're taking our measurements. Now, I just want to describe what's going on here inside of the concrete. Okay, so we have our anodic area, so our area of risk where we believe that corrosion is occurring. In this case, it appears that corrosion is occurring. We then have our hotspot, or our anode, which is on the anode is about negative 600 millivolts. Now, you'll note when we do the reading, our half cell is not touching the steel. It's effectively separated from the steel by the concrete between the steel and the concrete and the reference electrode. And so what we find is that the reading that we get on our voltmeter is actually the potential difference at the surface dependent on these potential lines coming out from our anodic area. So if we have quite a large cover, we're quite far away from the anode. In this position, we have a negative 220 millivolts reading. Now we move to the other position, same anode, less cover. Okay, so we're now closer within that field, and what we tend to find is that our readings are higher. However, that does not have any relation to the actual hotspot itself. And so if we had readings that were highly variable in terms of cover, then that could be problematic. It would also be problematic comparing high cover to low cover areas on a structure and just using those numbers. So resistivity, we'll talk more about resistivity later on, but effectively it's the conductivity of the concrete itself. So above here we had our field, we effectively had a constant resistivity. In this case, we could have a high resistivity, and that tends to not allow that electrical field to expand into the concrete itself. We could have a moderate resistivity in the middle here, where we do have some extension of the field into the concrete, and then we could have low resistivity where we have quite a large electrical field being created. Now, the instances here could be, if we have high resistivity, it's good quality concrete, it's got low moisture, low chlorides, all of those, we're just talking about the concrete itself. So it could be very dry, okay? Whereas we could approach the same structure and it's very wet. So this could represent the same structure, just at different ambient conditions. Now, the important point is that if we imagine that we have our reference electrode sitting on the surface here, and we look at how we're encountering that electrical field, we will get different readings. So that effectively means that the readings that you take on a structure could change quite substantially from season to season or from condition to condition on the structure. The last one, and you're going to have to bear with me, there are some relatively technical slides within this presentation. And for those of you who are here for the practical side of it, I'll try and keep some practical stuff, but I think it's also important to talk about some relatively technical points of view. And the reasoning here is that particularly this oxygen starvation is something that's encountered a lot on, say, marine environments where we have submerged concrete, and it effectively explains why we don't get the corrosion occurring below the surface that we tend to get above the surface. Okay, so let me explain the graph that we've got here. So we have this graph, and this represents our corrosion rate along the bottom, and then we have our potential across vertically here. We have these two curves, and they represent our anode and our cathode. Okay, where they cross is the current corrosion state of our structure. Okay, and at this point, we've got effectively sort of 0 millivolts and a very low corrosion rate. Okay, so this is a sort of this curve here is representing no chlorides, no carbonation. The effect of chlorides or carbonation directly affect the anodic reaction. And so what we tend to find is that, say if we added chlorides to the concrete through diffusion, then we would have a shift in this anodic curve. And what you'll see here is that as we increase the content, we get this shift of the curve moving down and down. And if you look at these points of intersection, these are now the current steady states of those systems. And so as we increase the concentration, we get an increase in corrosion rate. So this very neatly explains, why we can measure potentials and then make some sort of inference as to what's going on in terms of corrosion. However, when we decrease oxygen, so if we starve the system of oxygen, what we tend to find, and if you go back to that mechanism that I showed you, that it was the oxygen and the water that was going into the cathodic reaction, if we starve our system of oxygen, we get a shift in this cathodic curve. So we're moving a different effect, okay? And what we see here is that as our curve moves down, we're having decreasing oxygen, and the point that we intercept with this line is lower and lower. And if we just measure our potential differences, yeah, okay, we're getting lower potential differences. The effect of this, however, is that our corrosion rate is not increasing. And so, where we have this oxygen starvation, we could erroneously think that we have quite a high corrosion rate if we don't understand the mechanism, where we really don't. The test is not sort of indicating corrosion in this particular instance. So I've just given you a whole lot of explanations as to why the interpretation is quite difficult, and obviously, I think that just means that we need to learn more about how exactly what we're going to do and how we're going to face that. The first tool that we have in our toolbox is that when we're doing a half cell potential survey, we're going to grid up our structure, and we're going to take our measurements over the grid, and then we're going to create a surface map using that. If we go by AS 5100, I believe that's some sort of bridge repair standard, I might be wrong, then we should have our readings with a maximum of 300 millimeters. Now, what we should do is that if we have a greater depth of reinforcing, we need to make that grid spacing smaller, okay? If we have a high resistivity, again, we need to make that grid smaller, and that's just because if we make the grid smaller, we've got a higher likelihood of finding that region where we're directly over the anode as opposed to off to the side and getting major effects from that, that potential field not extending into the concrete. Some interesting sort of points here with regards to data collection on the PM8500 is that we've got our grid alignment here. So we've created our grid, and then we're going to put our reference electrode within that grid, and effectively all of our readings get gridded up. We could also use the wheel electrode. Again, it's just sort of showing here that if we're using this particular system, then we want to grid it up and then run our lines directly through the center of the boxes. And so we're picking up those same points in the center of the grid box. It can always be a challenge for figuring out exactly where your grid and where your readings align, and understanding where the datum point of that is. So that's a bit of a clarification point there. I guess the next point, after we could adjust our grids, the other thing that we can do is we can adjust how we interpret things. Now, one of my bugbears, I guess, is the prevalence of this particular standard out in the market, and so the ASTM standard, because of its, I'm guessing because of its simplicity, and engineers tend to like just having a hard and fast criteria, a yes/no criteria in terms of something. This criteria effectively says, if we get more negative than 350 millivolts, we have a 90% probability of corrosion. If we have less negative than 200 millivolts, we have a 90% probability of no corrosion. However, as I've sort of stated my case, this really bears no relation to any of the issues with regards to resistivity, cover, oxygen starvation. So it's very specific to one set of scenarios, and this is actually built from a data set from using, I think it was US Army bridges where they had de-icing salts. So you can imagine how different that is to the Australian environment. We have some international standards, such as this RILE-M, which I kind of like because it actually takes into account some of the environmental factors and gives you a sort of a number that we could shoot for corrosion in terms of what we're encountering in the environment. It doesn't tend to take into account cover. And then there's a totally different type of interpretation where we're not just using a set criteria, we're inventing the criteria from the data set. And so this is another one that's technically termed the double distribution interpretation. Again, this is going to get a little bit technical, but I'll try to explain it in the simplest terms. When we have corrosion, obviously we've highlighted that we have those anodic and cathodic regions. We could consider those as two separate data sets or two separate populations. Now, if we graphed those and we had enough of them, a normal population, we would tend to find that we would have two Bell distributions. And so that's what we're showing here is our distributions in terms of our voltages or our potentials for our active and passive regions or our anodic and cathodic regions, depending on which terminology you want to use. There is a crossover between them that creates our sort of our region of uncertainty. Okay, so if we take enough readings, then we would start to see this actually coming out of the data. Obviously, looking at this and doing all sorts of calculations can be quite difficult. So we have some fast steps that we can use to sort of speed the process up. So we've shown the same sort of, we've graphed all of our data in this histogram, which is definitely showing our two distributions. And then what we have is that we have our cumulative frequency, which is this black line here. And you can see that when it goes over each of the distributions, it has a particular gradient, and then when it's in the uncertainty area where the two distributions cross over, we have a different gradient. And so we can use these inflection points and use that just by looking at that graph and interpret where we would set our cathodic areas, anodic areas, and uncertain areas. We'd effectively set them at the inflection points. You have the ability to do that on a PM8000. You've got these passive and corrosion regions. You just basically move these with your fingers and point them towards where you believe the inflection points are. And then what it does is it creates a nice graph where the green region is the region above this, or the part of the data set that's above that. The red region is the corrosion threshold. So we've got all of this, all the red regions are sort of indicating that they're corroding. And then we have the yellow regions, which are relatively uncertain. So this really is the data set telling us what criteria we should use, and allows us to become independent of the environment that we're dealing with, whether it's high cover, resistivity, high temperatures, whatever. Although you'll note there's a lot of data here. So, you know, this doesn't lend itself to a 20-point data set. The next thing that we'll talk about is corrosion rates. So we do have devices that will measure corrosion rate or estimate corrosion rate, I think. And in particular, we're talking about the this particular method is specific to this Corro map. And so effectively what we're doing is we're applying a current shift, and from that we're assuming a corrosion rate. So the setup is basically the same as the half cell potentials. I have my connection to the reinforcing, going to my voltmeter. My voltmeter looks pretty specky. It's also got a galvanostat inside of there, and then data logging as well, so it's a bit more than just the voltmeter. We then have my other cable, and we're going to, the central part of this is a reference electrode. The additional elements that we've included in this test are that we have this counter electrode. And so what we're effectively doing is we're taking our reference electrode, our half cell potential, the same way that we did before, and then we're applying a small current and shifting the potential slightly, okay? And here we have some stats. We're trying to shift it by less than 20 millivolts, and we're varying the amount of current that we're providing, and we're doing it over about 10 seconds. So it can be a little bit of an iterative process. I promised some more technical slides. So if we look here, effectively what we're trying to do is calculate this I core. That's effectively what our corrosion rate is. And from that, we can make some determinations as to what the corrosion rate is. When we do our shift, we effectively have our potential, and then we apply our current and we get our shift. So we get this line, and this monstrosity of an equation here is effectively just predicting this curve. And you'll note that my RP is part of this. And we then basically assume a few of the other numbers, and some of them are part of the reading that we've actually taken, and we back calculate this number here using the curve that we've measured on site. And then this is called the Stern-Geary equation, but if you really look at it, it's effectively just V equals IR, which is a pretty standard electrical equation. V being the potential difference or the voltage, the V in this, we've got our R and we've got our I, and then we just use an assumed voltage dependent on whether it's corroding or not corroding. So you can see there's a lot of sort of fudge factors that go into this. And we'll talk about what that means in terms of interpretation in a second. What it looks like on the device as you take the measurement is you've got time versus potential difference, and we have our shift. And what we're effectively trying to do is that 20 millivolt shift. The reason why we're sticking to the 20 millivolt shift is because the relationship is relatively linear, and that means we can use this V equals IR here. Once it goes into another region, we wouldn't be able to use that. We can get some errors when we do this test, and so when we're looking at the screen, we're effectively looking at the shape of this curve and looking for any errors. Sometimes you can get spikes in it. They can be caused by issues with regards to not enough water, or a connection error, or providing too much current. What we're tending to do is that in our passive areas, we'll use a low current, because obviously we're just guessing the current at that point, trying to get a good graph. If we get a good graph, then we take that reading. If we find that our graph is not corresponding to what we expect, we might increase, say, the current. That might be in a corrosive area, so we need more current to be able to shift it. And so we just basically have that sort of iterative process. Interpretation. You'll see here that it's much more of a qualitative calculation, okay? Interpretation. And so what we have is we have these criteria. We have quite large bands of readings within these criteria. So if we have close to 0, we're going to have insignificant. If we have more than 15 milliamps per square centimeter, we're going to have a high reading. And then we've got a low and a moderate reading in between, this one representing a gap of, say, 10 milliamps. So we're generally not using it as a quantitative measurement. We're using it much more qualitatively in terms of, is it corroding quickly, or is it just not corroding? And I think that can really help when we're using our half cell potentials. We didn't want to use our double distribution method, but we understood, that a set criteria probably wasn't the best. If we just made it quite simple and said, I want to figure out whether my anodic areas are anodic, my most negative readings are, whether there's corrosion occurring there, then I could use this as a perfect way to use it. We do have, a way of calculating section loss. However, this is a spot measurement and it's not very accurate. And so it would be almost impossible to calculate our cross-sectional section loss using this measurement. Wouldn't recommend it at all. Obviously, you might wonder, which method I should use for different types of scenarios. Obviously, we go out to a lot of different structures to look at them and try to figure things out. They might have a treatment, they might be untreated, they could be wet, they could be dry, there could be inhibitors, there could be cracking delamination. We could have different types of reinforcing. This table here gives you a really good understanding of, which methods would be the strongest and which ones. I'm going to pull out the bottom one here and sort of point out from a practical point of view that if we have either an impermeable coating that prevents us from creating an electrical circuit with our concrete, that's a no-go. And second, if it's on the reinforcing, just as bad. And if the reinforcing is plastic, obviously we're not too worried about it. But yeah, that's a very good table there. So just sort of breaking it down between this half cell potentials and galvanostatic pulse method, we could use both, and they're both useful for finding hidden corrosion. We need to recognize that half cell potentials really only give a probability of corrosion. We can also understand that our galvanostatic pulse gives us an estimate, not a particularly accurate estimate of corrosion rate. Generally, the results that we get from a half cell potential survey is a map showing me the probable areas of corrosion. And then as I sort of highlighted there in terms of how we could use both of these methods as a hybrid method, once you've mapped it out, going back and actually measuring an anodic area, measure at an uncertain area, measure at a cathodic area, and put some surety to the numbers that you're getting. So the last technique that I'll talk about here is resistivity. I'd already previously mentioned it in earlier slides when I was talking about half cell potentials, and I sort of fudged over it and said that it was, the resistance of it. Effectively, resistivity differs from resistance in that resistance would be affected by the volume of material that we had, whereas resistivity is independent of the geometry of a piece of concrete. If you imagine, if we went and took a resistance meter and put it on either end of a small piece of concrete compared to a large piece of concrete, we would expect to get two different readings. However, the intrinsic resistivity of that material could potentially be the same, and it's just the size effects that we're measuring. So this is our best method by which we can determine effectively the conductivity of the concrete. And going back to that initial mechanism, obviously there was a lot of lines there where we had ions flowing through the material, and our resistivity or our conductivity would affect how those ions actually flow. So again, that does have a direct effect on the mechanism, not the entire part of the mechanism, but obviously a large part of it, and that's really what's affecting everything. So there's a few different ways that we can measure it. We could do a bulk electrical resistivity, or we can do a surface electrical resistivity. In the field, we tend to use a surface resistivity, merely because we only really have access to the surface. However, we could also take a bulk resistivity that's generally done on a core or a cylinder. It's more of a lab test, and it's effectively setting up, using a specimen itself. The advantages obviously of doing the surface measurement is that I can go up to any structure and I can take a reading. The first thing that I'll highlight here, and I'll need to highlight it several times, is the effect of moisture on the reading. It's highly affected by moisture, okay? And so we need to get a handle on the moisture state of our structure when we're taking this measurement. It is going to directly affect the results that you get, and you need to understand what's going on. There is a standard for surface resistivity, ASTM G57. Yet again, we don't have too much guidance from Australian standards when it comes to the measurement. Okay, I was just checking to see whether I had another diagram of this, but basically our surface resistance, we tend to use what's called the 4-point Wenner method, okay? So this is a diagram of this device here, but just showing you the working elements of it. We then have the concrete just here. So we have 1, 2, 3, 4 points, hence the name. And we're doing different things at each of these points. So on the 2 outer connectors, we're creating a current flow between, and then on the 2 inner, we're measuring the potential difference. And then we're using those two measurements to calculate resistivity along with the spacing between the points. Okay, so I sort of highlighted, I guess I'm gonna lay this on relatively thick with regards to moisture. You know, we've got some graphs here that show you the effect of moisture. And I think that, when you go into doing this type of measurement, the first thing you need to do is understand what your approach is going to be and, how you're actually going to take your measurements. The one moisture state that you can control quickly on a structure is saturation. Okay, it's relatively easy to get decent saturation into the surface of the concrete relatively quickly without too much effort, too much infrastructure, a hose or a spray bottle or something like that. So that's the one state that we can generally get to within an investigation. I always like to think of things in days. In one day I could definitely work out a scenario where I've saturated the structure, or my measurement points at least. However, what we need to understand there is that if it's saturated, that's going to be our worst case scenario. Okay, it's going to be our lowest resistivity. However, it does allow us to measure between one point and another point. And that brings to us the next point, is that if we can get moisture content out of the way, this graph indicates to us that resistivity gives us a very good understanding of whether we've got chloride-laden concrete or not. And chlorides, obviously, if we go back to the original mechanism, will destroy our passive layer. And so it is a good way of determining, how affected particular points on a structure are by chlorides. So imagining, say, power station just offshore. I'm here in WA, so I'm thinking of like Kwinana Power Station, something like that. It's right there on the beach. The different points on that structure, whether they're windward, whether they're in the splash zone, if they're in the seawater intake, all of those will have different exposures to chlorides, and we could get some sort of understanding of exactly how large an effect that would have on the structure from that. The probe spacing is relatively important. Obviously, when we're doing our measurement, imagine the scenario that this resipod here was in perfect line with the rebar just here. From that initial image, if we have a reinforcing bar just here, obviously that's going to affect first the current flow, but then also the voltage measurement that we take. And so that's not an ideal circumstance. Ideally, what we want to do is we want to miss the reinforcing if we can. So if we imagine just a standard, grid of reinforcing, the longest point within that is going to be obviously diagonal. And so if we could place our resistivity meter within that square or rectangle on an angle, not encountering any reinforcing, that's the ideal setup. If we can't do that, then we could bridge one, and that's going to be the smallest amount of reinforcing that's within that. We could potentially use a smaller spacing, and that's what this gadget here is for, giving us a variable spacing as opposed to the set spacing. However, we want to make sure that our spacing is appropriate to the type of concrete that we're encountering, and the main sort of thing that we're worried about is the maximum aggregate size. You could imagine that if you had quite a large aggregate and quite a small spacing, you might be on the same piece of aggregate, you're not actually measuring anything to do, or you're not sort of passing that current through the concrete itself. It's all getting locked up in that one piece of aggregate. Again, people tend to like to use relatively simplistic interpretations of these results, and so they're out there in the literature, and you don't shy away from them. However, they need to be used with an understanding that they're just generalized information, and they can give you an indication of what these actual readings mean. So there's obviously an inverse relationship between resistivity and corrosion rate. So we have low resistivities, we have high corrosion rate, we have high resistivities, we have low corrosion rate. Yeah, that's pretty self-explanatory, although they've put some numbers to it. There is another relationship that can be pointed out. So this RCP, or rapid chloride penetration test, which is a pretty popular test. We have sort of heard of it on some projects here in Australia, although we tend to use diffusion coefficients and a few other particular tests. And this data set indicates, and it's been proven because they're very similar tests, is that they correlate extremely well. So in a lab sense, there is a logic to replacing RCPs with resistivities. However, and then potentially you could use those out onto site, making sure that you take into account shape, size effects and things like that. So it could give you that link between your lab results and what's actually going out on site, particularly with new builds and quality control and all that type of thing. In an investigative term, not so much. Now here's one of the things that I think sort of negates, to a certain extent, what's shown here. So this is we're showing this as historic, and I think that the important thing to note here is that historically we just use Portland cements. However, over time, obviously we've started adding SCMs to our concrete, and we will continue to do so, and probably at a higher rate over time, because of our sort of trying to get to net zero and things like that. I think we're adding these SCMs such as, slag or fly ash or silica fume, or we've got many different SCMs coming onto the market these days. But the major thing to look at here is the effects that having these additional SCMs have on the results. So the SCMs tend to give much higher resistivity readings, not necessarily correlating to specific increases in corrosion protection. Okay, but then also we can note here there's the environmental effects as well. So we've got the material effects at the top, and then we've also got these environmental effects to the side here. This table here is from Reuben. That's I believe they're Dutch. I've shown a couple of slides or a couple of criteria from Reuben. It's quite a good organization if you're looking for references on corrosion tests. So resistivity is a measure of conductivity of the concrete. It's indicative of poor concrete, wet concrete, or contaminated concrete. It has a number of applications in corrosion investigations, such as corrosion rate estimation, measuring the cover of concrete. It's also used in cathodic protection installation. It can be used for many different other tests as opposed to just corrosion investigations. And obviously you've got to understand the correct way of doing these measurements. I did want to mention, I'm just thinking about it, there was one other thing that I wanted to mention here about the, on this slide here, the moisture effect. We would also take an ambient reading. So we're wetting down our structure and taking our worst case scenario, but before we do that, we will take an ambient reading, and we would include that in our data set. Okay, so thanks everyone for listening. I'm not sure whether there's room for questions or anything like that, but yeah, I'm glad that everybody's had an opportunity to have a listen.
We absolutely do have a little bit of time for questions. Is there anything in the room with us?
Yeah, so
hold on 1 second. I'm just going to pass you over. Give me a tick.
This is more about the products.
Sure.
Yeah.
If you can end your screen share, please, Reuben.
Yeah.
Yeah. So with the half cell measurement, do you have like your own off the shelf reference electrode that you use, or can we use our own?
You can use either or. So.
Yeah.
You've got the copper sulfate reference electrode. There's also a third-party connector that you can get. So
yeah.
You could use effectively any. You just need to know what you're using.
Yeah.
So you can use what you want.
Yeah. Okay.
So if you have a look at the product ranges we have, with with the PM8500, that comes with copper sulfate reference electrodes.
Yep.
So the rod electrode and the two different formats of wheel electrode are also going to be a match.
Okay, and who do we speak to about pricing?
We'll help out,
Yep.
or Joel will help out.
Yeah, no worries.
Do we have any other questions? No? Please keep that, just keep that a little bit away from the speakers, please. All right, Reuben. I'm just going to have a quick look on the chat as well. Oh, because...
Yep.
Yep, so we have on the chat, do you have any advice on how wet we should make the surface before taking a test? In some instances, we have found on site that the ResiPod takes some time to stabilise the resistivity readings.
Yeah, so the method that I've tended to use, and that's just been advised to me, is generally sort of wetting down maybe every 10 or 15 minutes, generally using a spray bottle or something like that, maybe over an hour or so. I don't think you need to, I mean, it's obviously going to depend on the spacing because the spacing controls how deep the test actually goes. So 50 mil spacing, 50 mil penetration. You're hoping to get penetration of water into the surface to the depth of 50 millimeters. That should be achievable over an hour, just saturating that spot and allowing the wicking process or the sorptivity of the concrete to actually draw that into the concrete. So, okay. Yeah, 4 or 5 spray downs over an hour.
All right, thanks so much, Reuben. Got one more question for you. Hold on.
How accurate is the measurements when you take them?
I can't hear it.
Oh, sorry. Yep, go down.
How accurate is the measurements that you get from the machine? Like when you... The PM8500, I think.
So I think the important thing to remember here is that obviously we always want to use a calibrated reference electrode and we want to use a calibrated half cell. And the reasoning, and a calibrated voltmeter. The reasoning for that is that obviously we want to be able to compare results and we want to be able to take results at different points in time. So that's an important point. However, I think the case that I've tried to build there with regards to resistivity and cover and those types of things is just the fact that the interpretation of the results themselves is really a function of so many things when we get on site. So plus or minus 5 millivolts is not really going to make any difference in terms of the interpretation that you make. However, obviously you can read the accuracy of the voltmeter. I think it'll be in the specifications of the machine. I believe it's going to be pretty low. I don't have the exact number off the top of my head. I'm sure that one of the guys in the room can find that number for you. However, in terms of the interpretation, it's not going to make any difference because your entire data set's going to be like that.
Sorry. Okay.
Yeah, so say if you have a known scenario, everything is calibrated, would the results from that be indicative of the actual, like what's happening or not? Or would there be like some margin of error?
So we're probably very much back to the kind of discussions we're having on other test methods, where if you want that much certainty in your understanding of the error in measurements, you start having to go to statistical methods, looking at the data set itself, evaluating where the uncertainties in your measurement tools are, and the standard deviation and the variation in your data, and actually calculate out the error. When you need that much certainty, it's not a supplier question, it's a calculate out what our sources of error are question.
No worries.
And I think that the other point there is that, we're talking about a probability of corrosion. And so I think that trying to combine accuracy or error of the measurement and sort of understanding that something is a probability of corrosion, there's a bit of a mismatch in the logic there in terms of what we're really trying to achieve with the methodology.
And we've got one more question, then I'm going to have to close it because I need to get ready for the next session.
No worries.
I mean, I might have some, I guess, comment to follow up
Yeah.
on Neil's question as well. It's more so like, you can also use it relatively as well.
Yeah.
You know, like if you have the same, wall of concrete or whatever, one bit's showing a value and then suddenly it dips down,
Yeah.
right? Even if the value itself, might not be, what you expect. But if there's a sudden change and everything else is the same, then okay, there's probably something goofy going on there. So it's not like so much the accuracy, but also like how much it changes relatively.
That's one of those, that's when Reuben's pointing out things like the double distribution method or just comparing a large data set and looking for variations. That's very much how this gets used in practice.
Yeah.
You find a region that has equal exposure, equal thickness, equal resistivity. It's predictable. You take a lot of data over it and you look if there's any local variations.
Yeah.
Did you have a question? All right, awesome. Thank you so much, Reuben. I'll let you go unless you'd like to sit on in the next session, and I will see everyone in a moment.